All right. So now we're going to start moving into our unit on energy balances. So energy balances are key to chemical reactor design. Chemical bonds store a lot of energy. So when chemical bonds are broken and formed over the course of a chemical reaction, this has the possibility to release a lot of heat in the form of heat of reaction. So to get a feel for this, thinking about the amount of energy needed to vaporize a mole of water, the heat of vaporization is about 40 kilojoules per mole of water. Now, if we were to go ahead and react hydrogen and oxygen to form water, that is going to give off about 240 kilojoules per mole of water. So a significantly more heat is associated with breaking the bonds in the hydrogen and oxygen molecules and forming the bonds in the water molecule than is associated with vaporizing liquid water into gaseous water. So the reason for this is the relative strengths of the bonds. So the physical bonds between water molecules are not as strong as the chemical bonds in molecules. Chemical bonds store a lot of potential energy, and the heat of reaction is due to that potential energy. So the example here, the water formation reaction, that actually has a pretty high heat of reaction, so not all reactions have that high of a heat of reaction. For example, some of the isomerization reactions that we'll study in this unit have lower heats of reaction, closer to that of the heat of vaporization of water. However, it's still important to consider energy balances. This is true even if the desired reaction is an endothermic reaction. We still need to understand energy balances. This is because we need to concern ourselves not only with the reactions that the reactor process is designed for, but also all of the reactions that could happen. So we will get to a unit later where we look at reaction runaway. Reaction runaway happens when the energy that's being released cannot be controlled. Many times that energy comes from a side process that wasn't part of the initial design. For example, we will look at a case where a solvent starts to atomize. So in that case, that reaction has a very high kinetic barrier, which kept it latent under normal operating conditions, but when something happened in the reactor that caused enough heat to be generated that the kinetic barrier was able to hop, and once the kinetic barrier was hopped, the reaction started producing heat very quickly, atomizing the solvent. So it's not just the reactions that we design for, but also all the other reactions that are possible. All of the chemical components in the reactor have a lot of potential energy in their chemical bonds, and henceforth we need to control for that. So to do that, we need to understand how energy balances influence reactor design. So that's what we're going to do here. We're going to derive an energy balance. In this particular lecture, we're going to derive the general energy balance, and then we will move on to derive energy balances for PFRs, PBRs, and CSTRs. Okay, so to derive the general energy balance, consider a system. So we're just going to consider kind of a generic system. So something maybe looks like this. So the general form of the energy balance is going to be the rate of accumulation of energy within the system equals to the rate of flow of heat into the system from the surroundings, plus the rate of work done on the system by the surroundings, plus the rate of energy added to the system by mass flow into the system, minus the rate of energy leaving the system by mass flow out of the system. So let's actually draw these contributions here. So the first one is the rate of accumulation of energy. That looks like this. The rate of flow of heat into the system from the surroundings, we're going to denote that with the letter Q. So I can draw an arrow in here and put Q dot because it's a rate of flow. This in a chemical reactor is usually coming from a heat exchanger or maybe a temperature exchange with an ambient atmosphere. Okay, work done on the system. So if it's being done on the system, then it's bringing energy into the system. So we'll draw the arrow pointing into the system. So this, for example, if the system is a CSTR, might come from a stir. I don't know of any other shaft work terms that affect reactor design. Mainly it's just the shaft work term. Of course, there's flow work. We're going to take care of that, though. That comes in the mass flow. So we have mass flow coming in and mass flow coming out. And in each component coming in, and each component is going to have an enthalpy associated with it. We'll say evaluated at in, and then coming out. And by using this enthalpy term instead of a internal energy term, we're embedding the flow work in there. So when we talk about energy, the only work term that we need to explicitly include is the shaft work term. So that's what that looks like in pictures. Symbolically, the energy balance looks like this. So we have accumulation is equal to the heat flow in plus the shaft work being done on the system, plus the sum of the molar flow rates times the enthalpies of the species coming in minus the molar flow rates times the enthalpies of the species coming out. The enthalpies, H's, are actually heats of formation, so they can be looked up. For an actual chemical species, they can be looked up. For example, I could go to the NIST chemistry web book and locate a heat of formation for a chemical species. Technically, the H's are heats of formation at the reaction temperature. However, while the heat of formation for an individual species varies significantly as a function of temperature, the heat of reaction does not vary that much with the reaction temperature. Therefore, it's more important when you construct your energy balance that you get the heat of formation than it is that you correct the heat of formation to the reaction temperature. So if you have the option to do one or the other, just get a heat of formation, even if that is at the standard conditions. One mistake that students make is they will look up the heat of formation for a particular species. They'll correct the heat of formation so that it goes up to the reaction temperature, but then in their energy balance, they'll just take that delta H between the standard and the reaction temperature. So that's a sensible heat change. That accounts for how the enthalpy of that species changes going from the standard temperature to the reaction temperature. But unless you include the heat of formation, you are not including all of the potential energy that's stored in the chemical bonds of the species. So that means that you're not accounting for the greatest contribution to the heat of reaction. So make sure that when you insert these heats of formation into your energy balance that you are using the heat of formation. Check the value, the magnitude of the value against the standard value. It should be on the same order of magnitude and relatively close to that value. Make sure that you are not inserting a much smaller value associated with the sensible heat change from taking the component from the standard temperature to the reaction temperature. Because if you do this, if you don't use the heat of formation, you are not accounting for the energy that is released from the chemical bonds as they break and form. Okay. So if you would like to see how this energy balance is derived, I encourage you to look at this interactive computer game, which is free on the University of Michigan website. There's two of them called Heat Effects 1 and Heat Effects 2. Those show how all of the different pieces to the energy balance come into play. They basically drag the different terms along the screen and they give a visual of the derivation. So if you are a visual learner, if you think that would be helpful, I encourage you to look at that. Okay, so going back to our energy balance, this is what the numerical form looks like. It's steady state, which a lot of what we do in this class is steady state. We'll get into some unsteady state towards the end of the class. But steady state, we're going to set the accumulation term to 0. And then the energy balance becomes Q plus W plus sum of the molar flow rates times the enthalpy is coming in minus sum of the molar flow rates times the enthalpy is coming out. So one of the implications on reactor design, there's several quantities that are dependent on the temperature. So when we write our reactor design equations, if we are doing non-isothermal reactor, we now have to write those terms as a function of temperature. So some of those quantities that depend on temperature, one is the rate constant. So K of T is equal to a value, K, given at some reference temperature. So what this means is sometimes you'll be given something like the specific rate constant is equal to 6 times 10 to the minus 3 at 298 K. In that case, this value would be 6 times 10 to the minus 3, and this value, T1, would be 298 K. So what we're going to do is going to take this reference value and we're going to multiply it by the exponential of the activation energy, E, divided by R. R is the gas constant. The activation energy here is going to have energy units, for example, kilojoules per mole. Because of that, we want to use the gas constant in units of energy per mole per temperature. So this is not the pressure volume divided by moles temperature value. This is the energy per mole temperature value. And then we're going to multiply this by 1 divided by T1, which in our case, this example was this reference temperature, which we said was 298 K, and then minus the temperature. So when I say reference temperature, I made this in this example up. I said that that was 298 K. It really depends on what temperature you're given a rate constant at. So it can assume a lot of different values. But anyways, this is a form of the Arrhenius equation. It's in the book. Other quantities that are dependent on temperature, one is concentration for gas phase reactions. So for liquid phase reactions, we assume the concentration is not dependent, or the dependence on temperature is minor. But for gas phase reactions, we know that the temperature influences the concentration. So this is our concentration equation. And we have been dealing with the influence of the change in the molar flow rate on the concentration, as well as the change in pressure due to pressure drop on the concentration. Now we're going to take into account the influence of temperature on concentration. So now when we write our concentration equations, we now need to include this term if it is a gas phase reaction. Similarly, temperature influences volumetric flow rate in a similar way as it does concentration, so I'm not going to write that out. The temperature influences the equilibrium constant. Kp. So we've been thinking about Kc in terms of concentration. The temperature dependence on the equilibrium constant is actually on Kp in terms of pressure. The equilibrium constant in terms of concentration versus pressure. Those two are related by a factor of RT. The relationship is given in the reference book. So Kp of T is equal to Kp1 T1, so again, some reference temperature, and again, we're going to have an exponential This time, the heat of reaction divided by the gas constant. And again, the gas constant will have energy units times 1 divided by 1 over the reference temperature minus 1 over the temperature. So the equilibrium constant is a function of temperature. So if we have a reversible reaction, this term needs to be included. To be honest, if we are looking at a non-isothermal reaction, a lot of times we have to worry about the equilibrium constant because once we change the conditions, we risk getting into a regime where the reaction is no longer irreversible. So an isothermal reaction, we can say it's irreversible because under the conditions it's being run, it's not, the reverse reaction isn't going to come into play. So if we're looking at a reaction that is non-isothermal, we might actually come into conditions where the equilibrium constant starts to favor the reactants over the products. So in that case, the reaction would start to become reversible. So that, because of that, it's good to account for the equilibrium constant and how it depends on temperature when we write our reactor design equations for non-isothermal reactors. Another quantity is the Ergun equation. So we have dP dW equals minus alpha over 2p T over T naught, which is something that we've not had to worry about. In isothermal reactors, but now this term comes into play. So now when we construct our Ergun equation, we need to make sure to include this factor in our equation. So the bottom line, when we do non-isothermal reactor design, there's several quantities that depend on temperature. We have been treating those as constants. If the temperature is changing, those terms are no longer constants, so we need to account for those in our design.